Keeping that strip heat off. Well, we have to have controls, and we also have to have the ability to heat the house using the compressor only down to 30 degrees. Balance point. We often hear the term balance point, and it's simply defined as the lowest outdoor temperature for which the output of the heat pump can heat the house by using the compressor only. Below that temperature, the strip heat is going to be needed to heat the house. If it's a gas backed up heat pump, usually it's economic considerations, price of gas versus the price of electricity, etc. Usually it's down to 40 degrees. So this is sort of an old school heat pump balance chart. The first thing that you do is that you do the heat loss calculation for the house, and you draw a line down to 65 degrees. And sure enough, the warmer it is outside, the less BTUs we have to pump into the house to maintain comfort. Let's plot our 2.5 ton system. So there's our capacity. We've simply drawn a line between capacity at 17 degrees and the capacity at 47 degrees. In this case, that 2.5 ton system would have a balance point of roughly 37 degrees. Too high for our wants. Let's see what a 3 ton comes in. 3 ton comes nicely in at 33 degrees. Let's see what a 3.5 will give us. 3.5 down to 28. That would make it a really good choice for the PTCS program. Sure, we could go larger, we could go 4 tons, but you know, it's going to cost more money. It might not add that much economic benefit, and the ducts probably aren't big enough to handle that much air. Another way of looking at heat pump sizing is just to recognize that if our goal is to have a balance point of 30 degrees, we really don't care about design temperature. We could actually do the heat loss of the house at 30 degrees, no matter where you are, in Port Angeles or Pocatello. It's still 30 degrees outside. So our house is going to have this heat loss at 30 degrees, and it's going to have a heat loss at about 30,000 BTUs at 30 degrees. Well, there's our 80K furnace, easily handles it, probably a little too big to tell you the truth. Our 5 ton system easily covers it. Our 4 ton system covers it. 3.5 ton system nails it perfectly. 3 ton, ooh, that auxiliary heat is really going to run. And by the time we get down to 2 and 2.5 ton systems, we can realize that we'll have lots of hours where the auxiliary heat is having to be used to keep the house warm. We hear a lot, why do we care so much about a balance point of 30? Why don't we make it 40 degrees? What this chart does here is it breaks the temperature in Boise, Idaho into 5-degree temperature bins. So this one right here is 40 to 45, this one is 45 to 49. What's really interesting is that there are 1,553 hours between 30 and 40 degrees in Boise every winter. That's equivalent to 65 days. So you'd be telling your customers, if you had a balance point of 40 rather than 30, that you're going to have to use your auxiliary heat 65 full days more than if you had a 30-degree balance point. Let's see what it says for Seattle. Seattle, as we all know, is a much warmer climate than Boise, but there are still 930 hours, and that's the equivalent of 39 days. So that's one of the reasons the program really pushes for that lower 30-degree balance point, because so many places in the Northwest spend a lot of hours between 30 and 40 degrees every winter. Northwest heat pump sizing, boy, we kind of get a break. We don't have humid climates. So if we oversize technically a little bit on the cooling side, we're not going to have too many comfort complaints to high indoor humidity. The good news is that in the Northwest, most of the time we have a heating dominated climate and not a cooling dominated climate, and it makes more sense to design for winter performance than it does summer performance. If you're really into reading ACCA manuals, Manual S says, boy, if you don't live in a humid place and you're in a heating dominated climate, you can use economic considerations. And there's been a lot of research done in the Northwest to prove that those economic considerations point to a target balance point of 30 degrees Fahrenheit. Which design temperature do you want to use? I have seen heat loss calculations turned in with using the wrong city. The most important thing you do is have to pick the right city. So in this case, what we're going to do is we're going to pick Portland, Oregon. And we'll take a look here at cooling. We see that the 1% cooling design temperature is 86 degrees. The 2% is only 83 degrees. If we go up here to the mean extreme, it's actually 99 degrees. The 0.4 is 90. Portland, Oregon has an unusual climate. Sure enough, only 1% of the time, historically speaking, has the summer design temperature been above 86. But your customers buy air conditioning for when it gets warm. And generally we see temperatures when people really use air conditioning around 95 degrees. My advice is don't be afraid of using the 0.4 cooling design temperature summer or the mean extreme. Now we have the official summer climate map of America. Down in the southeast, it's really hot and really humid. Your air conditioner down there really earns its title as being an air conditioner, because not only is it lowering the temperature of the air, but it's bringing all that humidity out of the air. Up in the northwest, it's not quite so hot, but it's still pretty muggy. Down in the southwest, it's just blazing hot. Rocky Mountain West, hot and really dry. And up here in the northwest, we sometimes get hot. Compared to the rest of the country, we're still pretty mild, but we do get hot, and air conditioning is becoming more and more popular, especially as we run into the 5th season, which is the smoke season. People are reluctant to open their windows and will rely on mechanical cooling systems. The good news is when we do get hot, we get dry. All we have to worry about is the sensible capacity of the air conditioner and not the latent capacity. Some more definitions. The total cooling load is a combination of both the sensible and latent. Sensible is that part of the cooling load that involves lowering the dry bulb temperature. The dry bulb temperature is just a regular thermometer. The latent cooling load, that's the hidden cooling load, if you will, it's a part of the cooling load that involves removing water vapor. The more water vapor you have to remove, the less the sensible capacity is. Some psychrometric definitions. Dry bulb temperature, that's the temperature measured by an ordinary room thermometer. It's also what the thermostat reads. This is sort of an old school non-digital psychrometer. You've got two thermometers in here, if you will. You have a dry bulb one and you have a wet bulb one. And there's a little cotton sock here and a water reservoir here. The sock wicks up the water and gets a wet cotton sock. And what the user of it would do would be to spin it around, and as you spin it around, water evaporates off that wet cotton sock. The drier it is, the more evaporation occurs, the lower that wet bulb will be. The wetter it is, the opposite occurs. So here in the Northwest, we often talk about having an ideal temperature split of 20 degrees. And sure enough, if we have a wet bulb of 62 degrees, which is common, and a indoor entering dry bulb of 76 degrees, 20 degrees is a pretty good target. But that's to say, some days we get out there and it's kind of muggy, and it's actually 68 degree entering wet bulb, and we have a 72 entering dry bulb. Our sensible split would only be 13 degrees. What's happening here is it takes quite a bit of, you're releasing quite a bit of energy when you turn all that water vapor back into liquid, and that lowers your sensible capacity. But Manual S says about cooling, don't oversize by more than 115% or 125% if it's a heat pump. We don't have to worry about that oversizing of air conditioner too much. Of course you can oversize air conditioners, but the reason they're so worried about that is dehumidification. And when we are 95 degrees, chances are that air conditioner is running a long time. It's not very humid outside, and as that air conditioner runs, it even dries the indoor air out more and more. So there's the nerdiest slide of today's presentation. It's called the C sub D, or coefficient of degradation. Newer heat pumps have a much lower coefficient of degradation. What that is the penalty you pay for short cycling. Newer systems, the penalty for short cycling, at least from an energy perspective, is not all that high. Manual says, what Manual S says about cooling, don't oversize by more than 115%. Why? I know I'm driving this point home because they're very concerned about dehumidification. Sizing for air conditioning. Okay, so we've got our load. Now we have to figure out what is going to be our best air conditioner to match the load of the house. Unfortunately, every manufacturer does these detailed capacity tables just a little bit different, making our lives complicated. But all of them tend to have at least this information, and the basic project is to find the outside design temperature. In this case, we're going to pick 95 degrees. That's pretty realistic. Determine your CFM. We're going to use 1200 because this is a PTCS job and we know we're going to get the correct airflow. So what that means, if you don't have 1200 CFM, if you only have 1000 CFM, these charts are wrong. Pick the lowest entering wet bulb, or EWB, if you will, indoor wet bulb right here. 59, that's a good one for us. And then locate the sensible capacity. Here we have the total capacity, and again, that's the sensible plus the latent. And here, our 3-ton machine is giving us 30K with the sensible capacity, which is really good. Please notice if we pick 67, the sensible capacity drops all the way down to 20, but the total capacity goes up to 37. I really urge you when sizing your air conditioners in the Northwest to pick the lowest indoor wet bulb you can. That's the best indication of the sensible capacity, that ability to lower the dry bulb temperature in the house. Manual S cooling, understand those two loads are separate. Again, what's interesting is in other parts of the country, if you have a leaky house, the latent load increases because of all the humidity outside. In dry climates like ours, that leaky home, actually the air is so dry that the leakiness actually dries it out further. There are 4 important things to remember when sizing for cooling. Again, once again, we live in the great Northwest where we don't have to worry about dehumidification. That's the good news. Air conditioning originally meant you have to reduce the latent load and the sensible load. And insulation of the house and good windows and good ductwork are probably the biggest factors that are going to influence the size of the heat pump that you put in. And I'm sorry, nobody likes to look at detailed capacity tables, but to pick the right system, especially for cooling, you really have to look at them. In summary, these are the items you sort of have to sweat the details a little bit on. Insulation levels, don't worry if it's an R33 or an R38. Doesn't matter that much, but none, some, or a fair amount sure matters in the ultimate size of the heat pump you put in the house. House tightness here in the Northwest, it typically ranges from 1/3 of an ACH up to 0.8. New construction is probably going to be closer to 0.2. If your software tells you have an ACH of 2, something is probably wrong. That would be a barn with the doors open on a windy day. Windows, our solar heat gain coefficient is absolutely critical. In the Northwest, if you know the U value, that say you have a U value of your window of 0.4, the solar heat gain coefficient is also pretty close to 0.4. A lot of software out there guesses a little too high at the solar heat gain coefficient, which pads the cooling load a little too much. Duct multiplier, typically between 5 and 20%. If it's worse than that, you really should fix it. It's hard to make people comfortable with heat pumps with leaky, uninsulated ducts. And insulation is just as important on that ductwork as making sure the air doesn't leak out of it. House size is often important, but as we said, R values and U values and ACH and duct leakage probably have a bigger role, but obviously the larger house, all the other things being equal, will require a larger system. Capacity of the heat pump, the desired balance point, we're using a 30-degree balance point. And again, you have to look at the detailed capacity tables provided by the manufacturer. And oh yeah, number 7, make sure you pick the right weather station. Well, thank you for listening to today's presentation, and this signifies the end.